Hi, I'm Herb Gross, and welcome to lecture number 26 in Gateways to Algebra, where today we're going to talk a bit about adding and subtracting polynomials. And that by itself is not going to be the real exciting thing. The real exciting thing is going to be to see just how closely this is related to place value arithmetic. One thing I hope to show you in the next several lectures is that if you really understood whole number arithmetic using place value notation, not memorized it, but understood it, there's going to be nothing at all new that you're going to be learning as we handle polynomials. In other words, if you say, I understand arithmetic, but I have trouble with polynomials, it means you don't really understand arithmetic, but rather that you memorized it. But before we get into that, let's just proceed from a more mundane point of view. Remember, when we're dealing with numbers, we say what? When you add two numbers, you expect the result to be a number. Well, we expect the same thing to happen with polynomials. Suppose I have the polynomial, and to indicate what polynomial I'm dealing with, I enclose these in parentheses. Suppose you had 2x to the third power plus 3x squared plus 4x plus 5. By way of review, that's a polynomial of degree 3. Here's another polynomial of degree 3, just by coincidence. It's 3x to the third plus 4x squared plus 3x plus 1. And I want to combine these into one polynomial. Well, of course, all I have to do is to remove the parentheses, and that makes us one polynomial. But remember what we agreed to do. We agreed to always group the terms and order them from the highest degree to the lowest degree. So what I do over here is here's an x to the third, here's an x to the third term. In other words, I take this term, and in my mind I think of that as what? 2x to the third plus 3x to the third. Why am I doing that? Because the 2 and the 3 are modifying the same noun, and hence what's in the parentheses here will simply be 5x to the third. Here is a 3x squared term. Here is a 4x squared term. I group them together, 3x squared plus 4x squared. Again, see what's happening. The 3 and the 4 are both modifying x squared, so we say the answer is what? 7x squared. Okay? Then I have a 4x term here and a 3x term here. 4x plus 3x is 7x. Then I have a 5 here and a 1 here. 5 plus 1 is 6. So in other words, the sum of these two polynomials is the single polynomial 5x to the third plus 7x squared plus 7x plus 6. And by the way, I didn't belabor the point, but notice how I just casually used the commutative and the associate properties of addition. I simply changed the order of these terms and regrouped them as I felt fit, because I can do that as long as the problem is what? Purely addition or purely multiplication. Let's do another problem and see what happens. Here I have a polynomial of degree 4 being added to a polynomial of degree 5. And I just want to do a couple of these to make sure you see the mechanics of this. What am I allowed to do? To regroup these any way I want. So I first look to see the highest degree term in here. And that's the highest exponent I see is a 5. There's only one of those terms, so I write that first. That's 2x to the 5th. Now what else do I see? As far as x to the 4th is concerned, I see a 5x to the 4th and a 3x to the 4th. And again, let me remind you, by putting these check marks here, later on when I'm through, I just look to make sure that every number is checked to make sure I haven't missed anything. Well, 5x to the 4th plus 3x to the 4th is 8x to the 4th. Here's a x to the third term. That's the only one there, so I put down 2x to the third next. Is there an x squared term? Yes, it's right over here. That's 5x squared. Is there an x term? Yes, that's 6x. Is there a constant term? A degree 0 term? Yes, that's 4. So the sum of these two polynomials is 2x to the 5th plus 8x to the 4th plus 2x cubed plus 5x squared plus 6x plus 4. And notice all the writing I did here to regroup these and the like. Let me show you now a form of place value. Let's suppose I let the first place be the 1s, the second place the x's, the third place the x squared, the next step the x to the third, the next step the x to the 4th, and the next step the x to the 5th. And by the way, does this remind you a little bit of place value? If instead of x I had 10 here, wouldn't the columns be 1, 10, 10 squared, 10 to the third, 10 to the 4th, 10 to the 5th? In other words, do you notice that place value is the special case of what we've written over here? when x is 10? We'll come back to that in a minute. But let's see how this works now. See, once I write these across the top here, notice how, see, the nouns are now taken care of by the column names. So all I have to do to write 5x to the 4th now is put a 5 in the x to the 4th column. See, where do I put this 2? In the x to the 3rd column. Where do I put this 4? In the 1's column. By the way, I could put zeros here if I wanted to, but is there any need to? See, as long as the nouns are present, I don't need the placeholder. I can see that I have no x squareds because the x squared column is empty. I can see I have no x's because the x column is empty. But I might want to make sure I put these zeros in just to remind me to make sure I'm putting the adjective into the right column. Now what do I do over here? The 2 goes into the x to the 5th column. The 3 goes into the x to the 4th column. Where does the 5 go? The 5 goes in the x squared column, and the 6 goes into the x column. I don't need the zeros here, but it's the same as if I had them. Now what do? The statement that says you can add the adjectives if they modify the same noun, notice that the same noun means you're in the same column. See, in other words, why can I say that 3 plus 5 is 8 over here? Because the 3 and the 5 both modify x to the 4th. Why can I put the 8 in this column? Because if the 5 and the 3 modify x to the 4th, so does the 8. So now what does the answer look like over here? It's 2x to the 5th plus 8x to the 4th plus 2x to the 3rd plus 5x squared plus 6x plus 4. Now, what I want to show you is, look at the resemblance between place value arithmetic and polynomial arithmetic. Suppose you were to walk into the room right now, you hadn't heard a word about what we were talking about, and you saw this problem, 234 plus 152 equals 386. Isn't it quite imaginable that you would read this as 234 plus 152 equals 386? Sure it is, because in your mind you're thinking of what? Ones, tens, hundreds. But instead of ones, tens, hundreds, suppose I was thinking of ones, x's, and x to the 2nd power, x squared. Now what does 234 mean? It's not 234, it's what? 2x squared plus 3x plus 4 ones. 2x squared plus 3x plus 4. What does 152 mean now? It means 1x squared plus 5x plus 2. See, 1x squared plus 5x plus 2. Now, how do you add these? You add the 1's, 4 plus 2 is 6. You add the x's, 3 plus 5 is 8. You add the x squareds, 2 plus 1 is 3. Isn't that exactly what you did over here? You said 2x squared plus 1x squared is 3x squared. 3x plus 5x is 8x, and 4 plus 2 is 6. This does exactly the same thing we did over here, but now there's no restriction as to whether this stands for tens or for whatever you want. In other words, could x stand for 10 over here? If x stood for 10, this would be what? 234 plus 152 equals 386. But x could stand for any number you want. In other words, what we're saying is that this simple algorithm, recipe, that we learned in arithmetic now works for any polynomial situation. For example, suppose I wanted x to stand for 4 instead of, suppose I wanted x to stand for 4 instead of 10. This would be the 1's place. This would be the 4's place. The next place would be what? 4 squared, x squared, which is 16. Look at what this says. It says 2 times 16 plus 3 times 4 plus 4 times 1 added to 1 times 16 plus 5 times 4 plus 2 times 1 is 3 times 16 plus 8 times 4 plus 6 times 1. And you see how this checks out? And if you translate this, this is what? 32 plus 12 plus 4, that's 48. This is 16 plus 20 plus 2, that's 38. This is 48 plus 32 plus 6, that's 86. And that's exactly the same answer you would get if you added these. Now, of course, I'm not saying that you have to put in all the zeros. You see, you can if you want to. What I'm saying is, look at this problem over here. I have 2x to the 6th plus 3x plus 1. And I want to add on to that 5x to the 7th plus 3. Well, the easiest way to tackle this is what? Obviously, the highest degree term is the x to the 7th. So that's 5x to the 7th. Then there's an x to the 6th term. That's what? 2x to the 6th. Then what else do I have over here? I have a 3x term. I also have what? 1 plus 3, which is 4. So in other words, the polynomial 2x to the 6th plus 3x plus 1, added to the polynomial 5x to the 7th plus 3, gives me the polynomial 5x to the 7th plus 2x to the 6th plus 3x plus 4. Now watch how I can do this if I wanted to do this by place value. See, what is the 2 modifying over here? It's the x to the 6th column, isn't it? Then this would be what? X to the 5, x to the 4. So you have no x's to the 5th, no x to the 4th, no x cubed, no x squared. What do you have now? 3 x's and a 1. See, once I put these nouns in here, I don't need these zeros, but the zeros, until I put these nouns in here, are reminding me of what denomination I skipped. And by the way, where would the 5 be now? That would be 1 column to the left of x to the 6th. See, how would you read this? There's a 5 in the x to the 7th place, and where's the 3 go? In the 1's place. And so these would be all zeros in here. Now what do you get when you add? 5, 2, 0, 0, 0, 0, 3, 4. And how would you read this answer? 5x to the 7th plus 2x to the 6th plus 3x plus 4. You see, you don't have to do the problem this way, but if you do it this way, it at least allows you to see more clearly without being blinded by all of the nouns up here what's happening. Obviously, if the degree gets too big, can you see the problem you're going to run into? See, if I had 2x to the 15th plus 3x squared plus 4, how would I write that in place value? There'd be a 2 here. Then I'd have to have what? Zeros in the x to the 14th, x to the 13th, x to the 12th, x to the 11th, x to the 10th, x to the 9th, x to the 8th. Do you see how long this would look? See, it's much easier to be able to telescope this and say what? I have one term that's 2x to the 15th. The next highest exponent I see is an x squared, and 3 of them and 2 more of them is 5 of them. Then there's a 5x term over here. Then there's a 4 and a 3 here, which is 7. By the way, there is one thing to be careful about when you're adding polynomials rather than place value. When a little kid who's just learned to add single digits is given a problem like 27 plus 35, what is the most common mistake that he makes? He says 3 plus 2 is 5, and 5 plus 7 is 12. In other words, he treats it as if it was 2 separate single-digit problems. And the teacher usually marks this wrong. If the kid were more sophisticated, he'd say to the teacher, why'd you mark this wrong? And the teacher would say, because the answer isn't 512. Whereupon the kid would say, I never said it was 512. I said you had what? 5 10s and 12 1s. See, if I put this line in here, do you see what's happening? See what's happening here? As long as the 10 column is visible, you do have what? 5 10s and 12 1s. Now, in place value, you can say what? I'll get rid of 10 of my 1s for 1 more 10. You can trade in 10 1s for a 10, so that would give you what? 6 10s and 2 1s. The problem is, once this becomes an x, you cannot trade in. In other words, the wrong way of doing arithmetic in grade school is the right way of doing it over here. See, what you're going to say is what? 2x, see, 2x plus 7 is the top number, 3x plus 5 is the bottom number, 2x plus 3x is 5x, 7 plus 5 is 12, and you cannot trade in because x is a variable. You're not trading in by 10s anymore, okay? By the way, another nice interesting thing about place value is when you come to subtraction. See, what is the traditional way of learning to subtract over here? The traditional way of learning to subtract over here is to say, okay, I can't take 4 from 3, so I'll trade in one of my 3 10s for 10 more 1s. So you now say what? 4 from 13 is 9, 1 from 2 is 1, and so the answer is 19. Now what I'd like to do is take a minute to show you a new way to look at subtraction. I'm not advocating that we do this. It's hard enough to learn to subtract without negative numbers, but we now have the luxury of knowing negative numbers, don't we? And what did we learn about negative numbers? That once you know negative numbers, you never again have to subtract. You can always do what? Add the opposite. Let's see how that would work back in this situation over here. Let's go back and look at the 33 minus 14 from another point of view. What did we say subtraction was? It was add the opposite. Let's change the subtraction to a plus and change the sign of all the digits in the bottom number. So this becomes what? Negative 1 plus 3 is 2. Negative 4 plus 3 is negative 1. I have it copied over here. So this would say what? You have 2 10s. Now we're not used to seeing negative numbers in place value. What do you think this would mean? A 1 over here would mean you add 1. The negative 1 over here means you subtract 1. So what do you have over here? 2 tens plus negative 1. See, 20 take away 1, which is 19. Isn't that the same answer you got this way? Okay, let's just do one more that way just to make sure we understand this. Suppose I say to you, subtract 567 from 1,234. Isn't the traditional method something like this? You say, well, I can't take 7 from 4, so I'm going to borrow. See, what I'll do is I'll put a 2 here and a 1 here. Now, I'm not going to be able to take 6 from 2, so I'm going to have to borrow again. And I'm not going to be able to take 5 from 1, so I'm going to have to borrow again. And you wind up saying what? 7 from 14 is 7, 6 from 12 is 6, and 5 from 11 is 6, and you get the answer this way. Now, I'm going to show you a new way to do this problem. I'm going to say, instead of subtracting 5, 6, 7, I'm going to add negative 5, negative 6, negative 7. Okay? Now let's do this by place value. See, 1 plus 0 is 1. 2 plus negative 5 is negative 3. 3 plus negative 6 is negative 3. 4 plus negative 7 is negative 3. Wow, we really rigged this one to have a whole bunch of negative 3's in here, but that's just a coincidence. Let's see what this number means now. You have 1,000. How many hundreds do you have? Negative 3. That means you're going to subtract 300. 300 from 1,000 is 700. How many tens do you have? Negative 3. That means you're going to subtract 30. 30 from 700 is 670. How many ones do you have? Negative 3. That means you're going to subtract 3 ones. What does that give you? 667. Are the two answers the same? They sure are. By the way, I'm not telling you not to do it this way. I want to show you what the advantage is in doing it this way. Up until now, as I did this problem, you thought I was taking 1,234 and subtracting 567. The surprise was I was reading these as what? 1s, x's, x squared, and x to the third. I had 1x to the third plus 2x squared plus 3x plus 4. And what I was subtracting was 5x squared plus 6x plus 7. You see, the borrowing method doesn't work here because I'm not trading in by tens anymore. You see, this is an abbreviation for what? 1x cubed plus 2x squared plus 3x plus 4. Okay? And what am I subtracting? 5x squared plus 6x plus 7. I claim that the answer is going to be x to the third minus 3x to the second power minus 3x minus 3. And let's just see how that works. Forget about that, what I've just shown you over here. Let's just do this problem by using the rules of arithmetic. How do you subtract? To subtract, you're going to do what? Add the opposite. And what's the best way of getting the opposite? Multiplying by negative 1. In other words, just put a 1 between the negative sign and the parentheses here. Now look what this problem looks like now. It's x to the third plus 2x squared plus 3x plus 4 plus negative 1 times the polynomial 6x squared plus 6x plus 7. By the distributive property, what do you do over here? The negative 1 has to multiply each of these three terms, and every time you multiply by negative 1, all you're doing is changing the sign. So the 5x squared becomes negative 5x squared, the 6x becomes negative 6x, and the 7 becomes negative 7. In other words, now what did we really do over here? Here's where these came from. See what happened here? The negative 5x squared came from changing the sign over here, the negative 6x from here, the negative 7 from here. In other words, the long way of doing the subtraction problem, if this was base 10, is the short way of doing the problem if we're using polynomials. See how you would read this answer now? It's 1x cubed plus negative 3x squared plus negative 3x plus negative 3, which is exactly the answer you got over here, isn't it? See, here's your x to the third. Here's a 2x squared plus negative 5x squared. See the abbreviation here? I didn't have to keep writing the x squareds because the column was labeled x squared. And by the way, again, let me remind you that all this really means when we solve this problem was this subtraction problem still means what? What did we have to add on to this to get this? In other words, the final check would be, how do you get from here to here? And you see what's going to happen? You don't have an x cubed over here, so you're going to have to add on x cubed. You have 5x squared, but you only want to wind up with 2x squared, so you have to have negative 3x squared combined with this. How do you get from 6x to 3x? You need negative 3x. How do you get from 7 to 4? You need negative 3. And again, this is how you would do the subtraction just by knowing addition. And see again, let's just do one more example to make sure we understand this. What must we add to 2x to the third plus 5x plus 7 to obtain 3x to the fourth plus 5x to the third plus 2x squared plus 3x plus 9? And the easiest way is to just look and see what you need. You want to wind up with 3x to the fourth. You don't have any, so you better add on 3x to the fourth. You want to wind up with 5x to the third. Okay, you only have 2x to the third, so you better add on what? 3 more x to the thirds. You want to wind up with 2x squareds. You don't have any x squared, so you better add on 2x squared. You want to wind up with 3x, but you already have 5x. That means you have to subtract 2x. In other words, you have to add on negative 2x. And you want to wind up with 9. You're starting at 7, so you have to add on 2 more. So this would be the answer to that problem without using the word subtraction. However, in terms of subtraction, I'm going to do what? Subtract this number from this one. And written in the language of place value, how is this number written? It's 3x to the fourths, 5x to the thirds, 2x squareds, 3x's, and 9 ones. This number here, okay, this number here starts with the x to the third place. There are no x to the fourths, 2x to the thirds. There are no x squareds. There are 5 x's and 7 ones. So I'm going to subtract this from this. Now, how do we subtract? The way we subtract is you change the subtraction to addition and change the signs of all these numbers. So 3 plus 0 is 3. 5 plus negative 2 is 3. 2 plus 0 is 2. 3 plus negative 5 is negative 2. 9 plus negative 7 is 2. Look at the coefficients. 3, 3, 2, negative 2, 2. 3, 3, 2, negative 2, 2. In other words, this method of extending the place value notation and using add the opposite to subtract allows us to do place value, polynomial arithmetic, just like place value. By the way, before we close today's lecture, I'd like to review something from arithmetic. One of these little puzzles I always like to show people about the kid who didn't know the nines table, and the teacher gave him this test in school, and he felt badly because he hadn't done his homework. So he said, gee, I know that 9 times 1 is 9, but that's all I know. So I might just as well correct the paper for the teacher because it's the least I can do for not doing my homework. So we counted the number he was going to get wrong. 1, 2, 3, 4, 5, 6, 7, 8. Then he said, gee, the way my luck is going today, I probably even counted wrong, so I better double check. 1 wrong, 2 wrong, 3 wrong, 4 wrong, 5 wrong, 6 wrong, 7 wrong, 8 wrong. And he passed the paper in, and what happened? He had a perfect score. A great story here. He didn't know what he was doing. Teacher didn't know what he was doing. He got 100. See, is this correct? Sure it is. Now, why did this work? The reason that this worked is every time you want to add on 9, a fast way of doing it is what? Add 1 to the tens place, but subtract 1 from the ones place. In other words, when you buy something for $9, how do you usually pay for it? You give the person a $10 bill, he gives you back a 1. So in other words, you're gaining a 10, but losing a 1 if you're the merchant. So you see what's happening over here? We let all of, as we go down this column, we add on 1 to the tens place each time, but we're also doing what? Subtracting 1 from the nines place. People say, gee, I wonder if that would work with 8s. Well, it doesn't. See, what's 8? 8 is 10 minus 2. So what you could do is what? I want you to see how the subtract, the add the opposite rule really works if you deal with negative numbers. I just want you to see that we could have done this. See what happens? Every time you want to add on 8, what should you do? Add on a 10 and take away 2 1s. So what happens here? I add on a 10, that gives me 1. Take away 2 1s from the 8 leaves me with a 6. Add on 1 more 10 gives me 2 of them. Take away 2 1s from the 6 leaves me with a 4. See what's happening? 8 times 3 is 24. How do I get the next 8? Add on 10 gives me a 3 here. Subtract 2 gives me 32 over here. Now, what do I do next? Add on a 10, subtract 2 1s. That brings me up to what? 40. What do I do next? Okay? Add on 10, subtract 2. That means what? Add negative 2. So the next one is going to be what? 5, negative 2. We're not used to seeing that in place value, but how would you read that now? It's 5 tens, which is 50, minus 2, which is 48, and there's your 8 times 6 equals 48. See? And you see how this thing is going again? Keep adding one more 10, subtracting 2 more 1s. And if you don't read this as subtracting, you're doing what? You're adding -2 each time. Now, what I wanted to show you by that wasn't just to have fun. What I wanted you to see is that the structure of place value arithmetic mimics the structure of polynomial arithmetic. So that if you really understood whole number arithmetic, you're not going to have any trouble with polynomial arithmetic. But what's even nicer about polynomial arithmetic is that it doesn't presuppose that you're trading in by tens. In other words, when you subtract by borrowing, the borrowing method hinges on what? That you're trading in by tens. If you were dealing in binary arithmetic, you wouldn't be borrowing 10, you'd be borrowing 2. But what's really nice about the add the opposite rule is you're never borrowing. When somebody says subtract 7, all you're going to do is what? Add -7 and let the negative numbers take care of themselves. And that brings up another interesting point, that after this series of lectures is over, there's a very good chance that even if you're having trouble with polynomials, you're going to understand whole number arithmetic a lot better. And that's another part that goes into the cycle of learning. And that is that sometimes we learn the prerequisite material better because it's being used as a means to an end rather than as an end itself in learning new material. So hopefully this is opening up some new horizons for you in terms of some of the material that came before. It's hopefully making some new material not seem too difficult for you. But again, before we go on to multiplying polynomials, you may want to review this till you're sure you understand it. But next time we will talk about multiplying polynomials. But until next time, study hard, have fun, stay young. See you soon.